Hey, Honors Chemistry, this is Thursday, April 30th, and I want to thank you right off for staying with me. I appreciate the fact that we can get into Redox, and they're on now page 631. So if you go to 631, we're just going to say no more on chapter 18, although there's a lot of good stuff back there. Are you on 631 yet? Of course, you always have your periodic table up for every talk, and you got this bad boy too. All right. So I'm on 631. It's called oxidation reduction, and of course it's abbreviated redox. Why don't they abbreviate it ox-red? I have no foggy idea. That's just the way it works. So I'm going to show you a chemical reaction right up front here, and I'm going to ask you what type, what category of a chemical reaction it is afterwards. Okay, we got two of them actually. We're going to go ahead with zinc. This is called mossy zinc, and of course, you know why it's called mossy zinc? It's because it looks mossy. Of course it does. And we're going to put a little bit in. You guys had a lab that you did this already. And we're just going to squish that down in there, that little test tube. In fact, you did make hydrogen this way. We're going to take hydrochloric acid and throw it on top of this. And we're going to make us some hydrogen. I'm just looking for a little piece here because I don't want to get too much excitement down here in my basement. We're going to take some full strength 12 molar hydrochloric acid, so it happens fast because I've only got a few minutes here. We're going to pour it in like a, I was going to say redneck, but I don't want to say that. Might offend somebody. We're just going to pop it right in there, and what's this coming out of here? This is hydrogen. You guys see the bubbling and all that? So we're causing a reaction here. We're going to gather some hydrogen, and after we gather it, we're going to go ahead and pop it. So let me get my popper ready to go here. All right, and we're going to go ahead and get that stick. This is the way I do it. I let it climb right on up the stick. There you go. Attaboy. And then we're going to go ahead and see if we've got any hydrogen in here yet. I'm in a hurry. Come on, guys. Oh, yeah. Oh, yeah. We got hydrogen. So we'll go ahead and show you that that right there is condensation of that water on the test tube. We're going to go ahead and move this out of the way. That's all I want to show you. Then we're going to start writing on the board. So the first reaction was hydrochloric acid, aqueous, and zinc. That was a solid, and we made zinc chloride. And if you looked in that test tube, you'd see it's black, not silvery anymore. It's a new substance. That's solid. And we released hydrogen gas. Okay, and so is it balanced? Well, let's find out. 1, 1, 1, 1, 2, 1. So we're going to go 2 like that. Oh, the zinc is 2 plus, and chlorine is 1 negative. And so we're going to need 2 of those. Chrissy Crossy says so. Now it's balanced. Everything is looking good. All right. What kind of a reaction is that right there? Single displacement? Correct. Single displacement. The zinc displaces the hydrogen because it is higher on the activity series table. Okay. What's the second reaction? Well, we took the hydrogen that we generated, gas, and we combined it with the oxygen that was in the air in the room, and we formed water. And it initially was gas, but as soon as it hit the inside of that test tube, it said, man, it's really cool here, and it condensed, and so we're going to call it liquid. All right. Now, 2, 2, 1, 2, 2, here we go, here we go. Now we're good to go. This first one was a single displacement. This one is a synthesis. Because you're taking these elemental forms and you're creating a compound. It's synthesizing. There's only one product, and that is water. So what are the 5 types of reactions that we had to choose from? We had synthesis. We had decomposition. Then we had single displacement. And then we had double displacement. I'm going to put it over here. And then we had combustion. So those are 5 types of reactions that we learned in an earlier chapter, back when you were just little kids. All right. Now I'm going to tell you that when you get to college, they're going to break down solution reactions, things that dissolve, into 3 categories. Precipitation, which is a double displacement. You remember that? Change your partners do-si-do, and one of them might be a compound that is a precipitate and precipitates out of the solution to the bottom. And the other one they're going to say is acid-base. You know, like hydrochloric acid and sodium hydroxide, and it's a double displacement reaction also. Okay, acid-base. And then the third type of solution reaction is going to be called redox. So can you see that those 3 types of solution reactions actually covers the 5 types of reactions we've already studied. Now, sometimes the single displacement, the synthesis is not a redox reaction, but these 4 tend to be redox reactions, and these 2 tend to be double displacement. There you go. And now the redox reactions are those that change the oxidation number as the reaction progresses. All right. The precipitation and the acid base are considered non-redox. They're non-redox. They happen to be double displacement, and they do not change their oxidation numbers of the elements as it progresses. Okay, let's read the oxidation states on page 671, these 9 rules that you've already learned early in the book, and you had a lot of fun with it, I'm sure. Rule number one, the oxidation number of any pure element is 0, like the oxidation number of sodium is 0. 2, the oxidation number of a monatomic ion equals the charge on the ion. So chloride, Cl negative, the oxidation number is -1. Number 3, the more electronegative element in a binary compound, that's for 2 elements that are combined, is assigned the number equal to the charge that it would have if it were an ion. The more electronegative element, of course, is the nonmetal. So one of the furthest to the right, top right corner of the periodic table. So the more electronegative elements are over here. Okay, and number 3 says the oxidation number of oxygen and nitrogen oxide is -2. So oxygen gets its way, it's more electronegative, it's further to the top, closer to fluorine than nitrogen is. Number 4, the oxidation number of fluorine is always -1. So if the compound is lithium fluoride, fluorine is -1, and lithium would be +1. Number 5, oxygen has an oxidation number of -2, unless it isn't a -2. And that's the case where it might be in a peroxide where it's -1, and sometimes it combines with fluorine, which is highly electronegative, and so it might become a +1 or a +2. That's number 5. Number 6, hydrogen is always +1, unless it isn't. And that's when it's combined with a metal, and so it'll be a hydride. We call those hydrides, and hydrogen would be -1 in that case. Number 7, the group 1, group 2 elements and aluminum, their oxidation numbers are +1, +2, oh, you can't see it, +1, +2, and +3. respectively. Okay, number 8. The sum of the oxidation numbers has to add up to 0 unless it is a polyatomic ion that has a charge. Number 9, in that case, it equals the charge of the polyatomic ion. All right, so that's the rules of oxidation numbers. Well, let's just go ahead and take a look at the oxidation numbers on this. We're going to say the oxidation number of this pure element is 0. That pure element is 0. And over here in the compound form, oxygen is always 2 negative or -2. Oxidation numbers, the negative comes first. And then the hydrogen is +1. And there's 2 of them. Okay, so we got an equation that's balanced by atoms. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. And they're balanced by charge. Over here, the charge adds up to 0. Over there, 2 times +1 is 2. And a -2, that adds up to 0. Okay, so balanced by charge and balanced by atoms. Has the oxidation number changed for hydrogen? Did it go from 0 up to 1? And how about for oxygen? Did the oxidation number go from 0 down to 2? Anytime the oxidation number increases, it's called oxidation. Anytime the oxidation number decreases, going from reactants to products, it's called reduction. And that makes sense because it's reducing. And the other one's getting bigger, so we call it oxidizing. And so if you have, if you look at the history of this term, the reduction comes from the idea that you take an ore, like iron ore, iron oxide, magnetite, and you put it in a blast furnace, and you basically melt it down, and the sludge comes to the top, and the pure iron goes to the bottom. And they pour off the sludge with this great big old scoop. And you're going to have nothing but iron left, and it's been reduced in the amount of mass that the ore weighed. The ore weighed this much, and the iron only weighs that much, and so you say that the mass has been reduced. When in fact, what happened was that the iron oxidation number went down, because in an iron oxide, Fe2O3, iron is +3, and oxygen is -2. When you break it down to pure iron, then it's 0, and going from +3 down to 0 is a reduction. That's the way we say it, but the history behind it is that it lost mass when it was in the blast furnace. And then the oxidation is when you burn something. It's combining with the, combining with oxygen in the air. And that's where that term came from. It's a combustion term. Okay, so let's go ahead and take a look at this upper equation and find out if we have any redox going on. This was synthesis, where hydrogen and oxygen made water. And this one up here is going to be single displacement. Both of those, synthesis and single displacement, were in the category I said that could probably be redox. It was only the double displacement ones that were not redox. Okay, which included acid-base reactions, and then the, what was the other one? Oh, precipitation reactions. Okay, so we got hydrogen and chlorine. Chlorine is -1. Hydrogen is +1. And that's why the subscripts are 1 and 1. Zinc is a pure element, it's 0. And then zinc is +2, and chlorine is -1, and hydrogen is a pure element. So do you see any redox? You bet you do. You see oxidation. Which one goes up? Well, it looks like zinc goes from 0 up to +2. That's called oxidation. And we say that chlorine remains the same. So we're going to ignore chlorine. And zinc and hydrogen goes from +1 down to 0. We're going to call that reduction. Now, what we do with this is we make half reactions. And the half reactions look like this. We say that HCl, let's go oxidation first. Let's go zinc. Solid zinc becomes zinc chloride. Or we can say 2 positive. Okay, and then we can say that the hydrogens become hydrogen gas. And so they go from +1 down to 0. And we don't have to have the oxidation numbers up there to show you that. Okay, so on this case, how do we balance the equation? We got 1 zinc, we got 1 zinc. It's balanced for atoms. How about for charge? Well, we got 0 over here and 2 plus over there. So the way we balance for charge is we add electrons. And electrons are negative. So if we have 2 negative electrons, and we have a 2 positive ion, 2 positive plus 2 negative is 0. And that's what we started with over here. Now, where do we add the electrons on this next half reaction? Well, we don't add it over here because 0, but we need to add it over there. Because here we got 2, positive 1, that's positive 2. And now we got -2, positive 2, -2 adds up to 0. And it should be this way. Each half reaction has the electrons on the one side and the electrons on the other side, so that they will cancel out when we add those reactions to get the original reaction. And this right here is oxidation. I'm going to go OX. And this is reduction. I'm going to say RED. Now the question is, what is it that's oxidizing the zinc? What is it that's oxidizing the zinc? It's the hydrogen. And so this is called the oxidizing agent. And what is it that is reducing the hydrogen? That's the zinc. It's reducing the hydrogen. And so we got the oxidizing agent, we got the reducing agent. The zinc reduces the hydrogen, and the hydrogen oxidizes the zinc. What do you mean oxidizes? Well, these 2 positive electron transfer. Redox is all about electron transfer. And so oxidation and reduction. These are called half reactions. And when you add them together, you get the original reaction. I think I better stop there, otherwise you quit listening to me. We'll come back to that tomorrow. See ya.